Good morning, everybody. I hope that the basics of the Lewis-Dot structure in the chemical bonding chapter is quite clear to all of you. Uh, today I'm going to just do two or three more structures, a little bit more complicated. Okay, and then finally we are going to go to the limitations of the limitations of the Lewis-Dot model, and then the introduction of the base-pair theory. Okay, so first of all, just let's try to draw the structure of, the Lewis-Dot structure of, suppose, this one, CH3, CO, CH3, okay, CH3, CO, CH3, okay, then HNO3, just 3 let us do at this moment, HNO3 and carbon dioxide. So first of all, CH3CO, CH3. So what is Lewis-Dot structure says that it has to be 8 electrons or 2 electrons in the outermost shell of the atom, or the valence shell of the atom, and that has to be represented by the dots. Okay, fine. So let us try to do it. C, H, 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 C, O, C. I'm just giving you the hint that how these bonds and all will be there. So you might be thinking that, sir, how do you know it? Okay, so we are going to come to know with the due time. So here C has got 4 valence electrons, 1, 2, 3 and 4. This C has got 4 valence electrons. I'm just drawing it in a different color so that you can understand that. 1, 2, 3 and 4. This C also has got this is 1, 2, 3 and 4. Okay, this C has got 4 valence electrons. Again, I am using the other color. 1, 2, 3 and 4. Now each hydrogen has got 1 valence electrons in it. Each hydrogen. This is hydrogen's valence electrons, hydrogen's valence electron, 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 and oxygen has got 6 valence electrons in it. So 6 valence electrons, 1, 2, 3, 4, 5, 6. Now our intention is to make them 8, right? Our intention is to make them 8 simply. Okay, so we are going to make it, as I told, by Venn diagram method, and let us try to make them 8. Let us just try to make them 8. I'm using some different colors so that it will be easier for you to understand this. So this carbon, you can see, if it is like this, see how many are there? 1, 2, 3, 4, 5, 6, 7, 8. The carbon is fulfilled. The hydrogen, this, or let me not write because I included the hydrogen over here, so I should not include the hydrogen over here. First let me do the hydrogen here, this hydrogen here, this hydrogen here, okay, and I will going to draw this carbon. This carbon is 8. Okay, then let us do this hydrogen, this carbon, suppose 1, 2, 3, 4, 5, 6, 7, 8. So I am taking 8 electrons over here. Fine. Then this oxygen, 1, 2, 3, 4, 5, 6, 7, 8. This oxygen has got 8 electrons. Fine. This carbon atom, again, this hydrogens, let us do 1, 2, 3. Okay, each has got 2. And the carbon atom now 1, 2, 3, 4, 5, 6 and 7, 8. So this is the structure of it. And if we draw the Lewis-Dot structure, we know the nature of the bonding now. What is the nature of the bonding? C, single bond H, single bond H, single bond H, C. Now what is this C? This is bonded with double bond oxygen, single bond C, single bond H, single bond H, single bond H. So this is the overall structure of this particular compound. I hope it is clear to you. As I told, with more practice it will be further more clear to you. The next one, let us do it for ammonia. nitric acid. Let us do it for nitric acid. So while doing the nitric acid again, I'm writing it like this. Nitrogen is the central one, OH, so HNO3, O and O. Again, I'm going to draw the electrons first. Valence electron of oxygen is 1, 2, 3, 4, 5, 6. 6 electrons are there. Here also 1, 2, 3, 4, 5, 6 electrons are there. Here also 1, 2, 3, 4, 5, 6 electrons are there. And let me draw it by the other color of nitrogen's electrons and hydrogen's electron. Nitrogen has got 5 electrons, 1, 2, 3, 4, 5 in its valence shell, and the hydrogen got 1 in its valence shell. Okay, so just as I told, just a little bit of practice. So this hydrogen, I want to make it 1, let me make it 1. This hydrogen, let me make it 1. So this hydrogen is 1. Fine, this hydrogen is 1. Let me make this oxygen 8. 1, 2, 3, 4, 5, 6, 7, 8. So this oxygen is also 8. Fine. This oxygen, let us make it 8. 1, 2, 3, 4, 5, 6, 7, 8. So this oxygen is also 8. This oxygen, let us make it 8. 1, 2, 3, 4, 5, 6, 7, 8. This oxygen is also 8. Okay. And this nitrogen, let us make 8. How can we make it 8? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. See? Is that the structure of the ammonia? Now, if we write down the bonding, we will find it very easily like this. This N is double bonded with the oxygen. You can see 2 pairs are shared, so double bonded with oxygen. This N is single bonded with this oxygen, a single pair is shared. And this oxygen is single bonded with hydrogen. But what about this nitrogen and this oxygen? There is 1 pair shared. And this pair of electron is given by nitrogen for sharing. So this is not a pure covalent bond. This is a coordinate bond. And obviously we are going to represent it like this. N arrow O. Okay, so that's a coordinate bond where the pairs of electrons are donated by nitrogen for sharing. I hope it is clear. Okay. The last structure we are going to do, as I told you, must practice the remaining, and some more obviously we are going to do in the next theory also. The next structure we are going to do is for carbon dioxide. Now, for carbon dioxide, the molecule will be having the bonding between carbon, oxygen and oxygen. So carbon has got 4 electrons, we know 1, 2, 3, 4. Okay, 4 electrons of carbon are there. Oxygen has got 6 electrons in its valence shell. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now it wants to become 8. This wants to become 8. Sorry, everyone wants to become 8. So I will make this oxygen 8. How can I make this oxygen 8? This is oxygen's 8 electron. This is oxygen's 8 electron. And obviously this will be the carbon's 8 electron. Fine. Carbon's 8 electron. Fine. A simple one. So here the nature of the bonding will be what? The nature of the bonding will be C double bond O and C double bond O. Okay, so the structure of carbon dioxide is like this: C double bond O, C double bond O. Okay, that's the structure of the carbon dioxide. I hope everybody understood that. But the next thing we are going to do is that certain more structures of certain compounds of which are stable, but we'll try to find out by the Lewis dot structure. Okay, the first one we are going to do it for BeCl2. BeCl2. Okay, so I'm just rubbing it off. BeCl2. Just let us try to do it. BeCl2. Beryllium chloride or beryllium dichloride. Beryllium has got total 4 electrons. We know this. So if there are 4 electrons, the valence shell will have 2 electrons. So I'm just trying to draw it. beryllium has got 2 valence shell electrons, and each chlorine has got 7 electrons each in its valence shell. So chlorine 1, 2, 3, 4, 5, 6 and 7. Another chlorine 1, 2, 3, 4, 5, 6 and 7. This chlorine is becoming 8. This chlorine is becoming 8. But what about beryllium? Beryllium is becoming only 4. Though this particular molecule is very much stable, but it could not be explained by Lewis dot model. The central atom of this molecule is having less than 8 electrons. And this is the first limitation of the Lewis dot model. And that is called the first limitation. I'm writing over here. The first limitation, and that is called incomplete octet. We call it incomplete octet. Incomplete octet. Okay, that's the first limitation of Lewis dot model. I'm taking another example. BF3, boron trifluoride. Just try to understand this. Boron trifluoride, BF3, which is also existing very much stable compound, BF3. Let us try to explain this in terms of Lewis dot theory or Lewis dot model. Boron has got 3 electrons in its outermost shell. 3 electrons in its outermost shell. Fluorine has got 7 electrons in its outermost shell. 1, 2, 3, 4, 5, 6 and 7. Each fluorine 1, 2, 3, 4, 5, 6 and 7. Each fluorine has got 7 electrons in its outermost shell. Okay. Now we can very easily make the fluorines 8. Very easily we can make it 8. That's very much following. But what about boron? The boron is having only 6 electrons in its valence shell. So that is again an example of incomplete octet, which is not supported by Lewis dot model, but the compound as a whole is very, very stable, very much stable. I hope we could understand this type of limitation of the Lewis dot model. Let us do one more. PCl5, phosphorus pentachloride. Phosphorus pentachloride. Let us do it. PCl5. So phosphorus has got 5 electrons in its outermost shell. So 1, 2, 3, 4 and 5. 5 electrons in its valence shell. Now each chlorine has got 7 electrons in its valence shell. You know this. Each chlorine has got 7 electrons in its valence shell. 1, 2, 3, 4, 5, 6 and 7. Each chlorine 1, 2, 3, 4, 5, 6 and 7. This is one chlorine 1, 2, 3, 4, 5, 6 and 7. This is one chlorine 1, 2, 3, 4, 5, 6, 7. This is one chlorine 1, 2, 3, 4, 5, 6, 7. The chlorines can be very easily 8. It can be very easily 8 by just sharing 1 electron from phosphorus. But what about phosphorus? If you see phosphorus, it is making a bond with 5 chlorines and there are 5 bonded pairs of electrons, right? So there are total 10 electrons or 5 pairs of electrons present in the phosphorus valence shell. That means here the number is more than 8, but still the complex is, or still the compound is very much stable. This is another type of limitation, and this type of limitation is called, the second type of limitation is called expanded octet. Is called expanded octet, where the number of electrons of the central atom is greater than that of 8. Okay, I'm taking one more example of a stable compound, and that is SF6. That is SF6, sulfur hexafluoride. SF6, sulfur hexafluoride. This is also a stable compound. Let us try to draw the Lewis dot structure of it. Sulfur has got 6 electrons in its valence shell. So I'm going to draw 6, 1, 2, 3, 4, 5 and 6 electrons in its valence shell. There are 6 fluorines which has got 7 electrons each in its valence shell. So fluorine 1, 2, 3, 4, 5, 6 and 7. Fluorine 1, 2, 3, 4, 5, 6 and 7. Fluorine 1, 2, 3, 4, 5, 6 and 7. Fluorine 1, 2, 3, 4, 5, 6 and 7. Another fluorine 1, 2, 3, 4, 5, 6 and 7. Another fluorine 1, 2, 3, 4, 5, 6 and 7. Very easy to make the fluorines 8. Very easy. Okay, so we are making fluorines 8. But what is happening to the sulfur? Sulfur is having now 6 bonded pairs with 6 fluorines, right? 6 bonded pairs with 6 fluorines, sorry. 6 bonded pairs with 6 fluorines. And as a whole, there will be how many? As a whole, there will be 12 electrons. So this is again an example of expanded octet. That's the second limitation, you can say, of the Lewis dot model. Now, one more limitation is there. For example, suppose we want to explain the structure of NO, nitrogen monoxide. All of you know that the nitrogen monoxide is a stable compound and that exists, or nitrogen dioxide, whichever, let us take it as NO, nitrogen monoxide. Okay. Now, we won't even try to do it by the Lewis dot structure. Why, you know? Because nitrogen has got 5 electrons in its valence shell. Oxygen has got 6 electrons in its valence shell. So there are total 11 electrons in the valence shell, which is obviously an odd number. 11 electrons is in the valence shell, total number of electrons, which is an odd number. So that odd number by no means we can just divide them as octet or duplet. Simply we cannot do this. There will be always an excess or a less amount of electron. Okay. So this type of system or this type of molecules where the total number of valence electrons is odd also could not be explained by the Lewis dot model. And that's the third limitation of Lewis dot model. What is that? Odd electron molecules. Odd electron molecules could not be explained by the valence dot theory. So these are the limitations of valence dot theory, and these limitations were tried to overcome by the next accepted theory, which is known as, now we are going to that, that means we are just going to know about the basic of it, the theory of it. Then in the next class we are going to do it with the detail of it. So the next theory, which was actually ready to overcome these limitations, okay, or tried to rather I should say overcome these limitations, is called valence shell electron pair repulsion theory. Valence shell electron pair repulsion theory. This is the theory. Okay. In short, we call it VSEPR theory. VSEPR theory. Valence shell electron pair repulsion theory. Now, from the name itself, we can understand this. But before this, we must know one fact, that is, what is the, who proposed this valence shell electron shell repulsion theory? It is proposed by Sidgwick and Pauling. So sometimes one more question comes, we should know this. Sidgwick and Pauling has proposed this. That's first part. The next part is that valence shell. Whose valence shell? The valence shell of the central atom. The valence shell of the central atom. Electron pair. You know, electron pairs are there in the valence shell of the central atom. there can be two types of electron pair present in the valence shell of the central atom. Okay, one we call bond pair, one we call lone pair. Bond pair means we also know about this. Bond pair means the pair of electron which is responsible for the bond formation, and the lone pair means which is not taking part in the bond formation, but the electrons are present in the valence shell. Now this bond pair and lone pair, whichever are present in the valence shell, they are all repelling each other. Obviously, the electron pairs will repel each other. Now what does that is valence shell electron pair repulsion? First, the words is clear. Next, what did this theory say? This theory says that the valence shell of the central atom is considered as a sphere. Just think or imagine a ball, a football. It is think as a sphere. The valence shell of the central atom is considered as a sphere. Fine. Now the electron pairs, that is the bond pair or the lone pair in it, are, according to this theory, placed on the surface of the sphere. Placed on the surface of the sphere. Here, wherever. Okay. Now, this theory says that, obviously they are going to repel each other. This theory says that the electron pairs on the surface of the sphere of the central atom, valence shell, will be placed themselves in such a way so that they will experience the minimum repulsive force. They will experience the minimum repulsive force. Okay. So what is the first point? Let me just note it down. What is the first point? The first point is that the valence shell of the central atom, valence shell of the central atom is considered as sphere. That's the first point. Valence shell of the central atom is considered as sphere. That's the first point. Okay. The second point is what? The second point is that on the surface of this sphere, the electron pairs are present. Electron pair means the lone pair or the bond pair. Okay. So electron pair, the lone pair and the bond pair are present on the surface of the sphere. On the surface of the sphere. That's the second point. Hope you understood that. Now, they will be placed in such a way, this lone pair and bond pair will be placed in such a way on the surface of the sphere